I think I would like to do this question on the board to get the good, clear explanation, and I can move very fast. Okay. First, we will read out this. So there are three compound X, Y, Z coordination compounds. Okay. They have an octahedral geometry. So you have to understand in X, Y, Z, there should be 6 ligands in the inner coordination sphere. If this is metal M, so there should be 6 coordination number 6, and there can be some other charges outside. Oh wait, we don't know. Anyway, there should be 6 in the inner coordination sphere because the geometry is octahedral. The atomic composition of species in the coordination sphere X, Y, Z are given. Okay, so we'll use this board. Right, so we have let's say X, Y, and Z, and I will just check the question. So we have in the X we have Fe, H, and don't forget this is given in the coordination sphere, right? Fe, H10, Cn, oxygen 5, and sulfur. And in Y they have given same Fe, H8, C2, N2, O4, S2. And in Y, Z, they have given in Z, Fe, H6, C3, N3, okay, O3, S3. So these are the composition of the ligand elements in the coordination sphere, which is this. That is what they have given, right? So don't forget what they have given is this. And furthermore, if I go furthermore towards the question, the oxidation state of the metal ion in all three compounds is same. In each compound, 2 types of ligands are coordinated to the metal, and if these compounds contain non-coordinated anions, they are of the same type. So this is very good. They're telling one additional important information. So the oxidation state of ion here, it should be same. So it should be +2, +2, +2 in XYZ, or either +3, +3, +3 in the XYZ. Because we know common oxidation state of ion is either +2 or +3, right? So this is first point. And they say if these contain anions, they are of same type in each. And within the coordination sphere, they say in each compound, 2 types of ligand are coordinated to the metal. So this contain only 2 types of ligands. So these are the piece of information that they have given. Sorry. According to the question, right? So these are the things that they have given. So if these compounds contain non-coordinated anions, they are of the same types, which they are telling non-coordinated means they are telling if this has these outer counter ions, this also could be in the same type. This one, not this one. These 2 types. Now we will come to the further discussion of this. An aqueous solution is containing X, Y, Z in the 1:1:1 ratio. So we have a solution where this molar ratio is 1:1:1. Very good. And the concentration is 0.1. So this concentration of each of these species is 0.1 m, 0.1 m, and 0.1 m. So very good. And then they say when an excess AgNO3 solution was added to 100 cubic centimeter of S, okay, so we are going to use 100 cubic centimeter of this. Molar ratio is also given, that is 1:1:1. So the moles, number of moles are same. Then, right? So you add AgNO3, a yellow precipitate is formed. Okay, so we add AgNO3 and a yellow precipitate is formed. And the precipitate weight is given as 7.05 grams. And the precipitate does not dissolve in conch ammonia. So it's very simple, right? Because we have AgCl, AgBr, AgI. This is white in color. So if I stop this screen. So if you add AgNO3 to this particular solution, think about this. We are getting a yellow precipitate which is not dissolved in conch ammonia automatically. This is AgI. Okay. Otherwise, the only two yellow precipitate that is possible is AgBr and AgI, and they have given the molecular weight of this one as 235, the yellow precipitate, which is equal to this. So, because if you know Ag as 108, you can automatically get iodine is 127, so this is 235 point something. Okay, so this piece of information is also given. Now let's go to the question. Right, so they have given, you see, identify the ligands coordinated to metal ions X, Y, and Z. So we have to identify these ligands. So we will do that first. So what you have to do first here, without trying to get what ligands might be present, try to observe the elemental composition here. I see oxygen, 5 oxygen here, and I see 10 oxygen here. So how many water molecules it can form? It can form 5 water molecules. And in same here, I see 4 oxygen and 8 hydrogen. So it can form 4 water molecules. And here 3 oxygen and 3 hydrogen. It can form 3 water molecules. So here 5 water molecules, 4 water molecules, and 3 water molecules. So if the ligand is water, it can be. So if you remove water, here H10O5, you are remaining with carbon, nitrogen, and sulfur. And you know, in the question they have given, there can be only 2 types of ligands. So if one is water, the other one should be something that is combined with carbon, nitrogen, and sulfur, which is SCN minus or NCS minus, thiocyanate or isothiocyanate. It can be both. You understand what I am trying to tell? Otherwise, if you think this is as CN minus, you have to combine this hydrogen and oxygen and sulfur and try to make another ligand, because there are only 2 types. Okay, so you do anything, but the only acceptable thing is there should be only 2 types of ligands. You can get hydride as separately, or either CN as separately, then oxygen as separately, or even OH. You can have OH, so OH and SCN, so they will be all negative. It's problematic, right? So try to analyze based on that. The simplest possible way is to get water molecules and either thiocyanate or isothiocyanate, because SCN minus 1 and NCS also minus 1. The only difference is SCN is from the coordination from ligand, NCS is coordination from sulfur. That is the only difference in the coordination sphere. So the idea here is, let's try to analyze using that. So first X, so Fe, then we will have hydrogen H2O, and let's take this one, SCN. So we will put H2O5 and SCN. This is one, right? And with Y, it could be Fe H2O4, because I can see 4, and you see, if I take SCN, there are 2. Now it's octahedral, very nice. Here also octahedral, 6. So SCN2, right? And with the third one, Fe H2O3 SCN thrice. This is also very nice. You see, I can easily make the octahedral complex when I use water and thiocyanate or isothiocyanate. 666 in the inner coordination sphere. I'm done with drawing the structure. So my ligands in X, Y, and Z, that is what they have asked in the first question. So in the first question, they are asked what are the ligands. So identify the ligands. So according to this piece of information, my ligands actually are SCN minus, NCS minus, or either it could be water and NCS minus. Okay, you can write either H2O, you can write H2O, SCN minus, or NCS minus. There should be and here, right? Because water and SCN minus or NCS minus. So this is done. Write the chemical formula of the yellow. So yellow precipitate is surely should be silver iodide, AgI. Giving reasons, determine the structure of X, Y, and Z. So now we have come to a point, very important point. Because from the explanation, so we have come to 3 different structures for X, Y, and Z. But here we have not given the charge. Because when you add AgNO3 to this solution, to get AgI precipitate, there should be some counter ions with iodine here to give this AgI precipitate. So you have to understand here what should be the oxidation state of this ion and how many iodide atoms are present in each of these compounds. Okay, so try to get this one. So how to get that? The simplest way to get this as an idea, you count the number of moles of these 3. This one will be 100 into 0.1 into 10 to the power minus 3. So all these are same. Each moles are same. And then you try to get the number of moles of AgI, which should be equal to the number of moles of I minus that is given from these. Because it should be same, right? So when you want to get the number of moles of this, you can divide 7.05 by 235 grams per mole. You will see this one will be 0.03. When you divide this, you will get this as 0.03, right? So if you get this one as 0.03, this one will be 0.01, 0.01, and 0.01 moles. Okay. Now think, you have 0.01, 0.01, 0.01, and you have iodide minus that is given from each of these structures. The total amount is 0.03. So this 0.03 can be from 0.01 mole from this, 0.01 mole from this, 0.01 mole of this. And when you add these 3, it can be 0.03. Because total moles is iodide. Otherwise, this could be from 2 moles of iodide from this compound, 1 moles of from this compound, 0 moles of this one, so 0.02, 0.01, 0.03. So there are many combinations. So how to tackle that one? The simplest way to tackle that point is this. I will erase this one now, these things. Okay, so we have 3 different structures. Now think, these are 0.01 moles. So the precipitate AgI is 0.03. So I minus moles is 0.03. So we have to find this 0.03 somehow, right? So X is this. Now think about, if this is plus 2, this should be plus 2 and this should be plus 2, the oxidation state of iron. Because they say in our description, the oxidation state of iron cannot be changing in any of these compounds, right? So if this is plus 2, SCN is minus 1. So plus 2 minus 1 is plus 1. So there should be one iodine here to form the silver precipitate. So the amount of iodine that is given from this is 0.1 mole because stoichiometry is same. And if this is plus 2, this is minus 2. So the overall charge is 0. So there is no iodine from this one. Okay. And if this is plus 2, here this is minus 3 from SCN. If this is plus 2, this should be minus 3 from SCN minus. Okay. And minus 3 means there should not be like this, right? There should be a negative charge because we don't have anything to put iodine. So think about that fact. And in the same way, if you try to combine like this, FeH2O6, SCN, if this is plus 3, if this is plus 3, FeH2O6, sorry, not H2O6 here. This is H2O5 here, H2O4 here, CN2 here, and this is X, this is Y, and this is Z. Fe H2O3 SCN thrice. Now we will think in a different way. If all these are plus 3, so if this is plus 3, here this should be minus 1, so the overall charge is plus 2, so I2. So if you use 0.01, this is 0.02 because there are 2 iodines, so 0.01 into 2 is 0.02. And if this is plus 3, so minus 2 plus 3 plus 1, so there should be iodine, so 0.01. And here this is plus 3 minus 3, the overall charge is 0. So I can see here, this combination is a little bit tough to accept because it only gives 0.01 moles of iodide for the precipitation. But here, if you think the oxidation state of iron is plus 3, this one will give 0.02 moles. And this one will give 0.01 moles, which is very nice because my overall precipitate I have is 0.03. So these are the structures of my compound. Okay. So there is not much of rocket chemistry here. This you need to understand the fact. That is, they have given from the description. That is very important to understand. Right? So try to analyze how we go through this question. We look at the number of moles of this. They have given the concentration and the amount that is used in 100 cubic centimeters. So we know the number of moles of each of these. And we first try to calculate the moles of the precipitate, and it was 0.03. And based on that information, we try to get this oxidation state of iron as plus 2, plus 2, plus 2, or either plus 3, plus 3, plus 3. And if you think that as plus 2, 0.01, that's it. But when you get this as plus 3, plus 3, plus 3, you see there is 0.02 and 0.01, which should be the addition that gave us the total amount of iodine as 0.03 as AgI. So these are the structures. That is what they have asked in the question. Draw the giving reasons, determine the structures. So to give the reasons, what you can do here, you find the amount of the precipitate of AgI, show that as 0.03, and then you explain when I get this oxidation state of iron as plus 3, you can explain the amount of iodine that is given from this structure is 0.02, Y 0.01, and Z does not give anything. So the total number of moles is 0.03, which is acceptable. Okay, so you can explain that nicely. And the last one, given below is the structure of ethylene diamine. Yes, so this is En. So this can be coordinated to this nitrogen and this nitrogen, En. Ethylene diamine coordinates to the metal M3 plus through two nitrogen atoms. So that is what I have mentioned here. Form the complex Q. The metal ion and ligand coordinated Q has an octahedral geometry. So we did a similar type of question in the previous past paper as well. Write the structural formula of Q and draw its structure. So consider that only ethylene diamine is coordinated to the metal ion and use abbreviation En to denote ethylene diamine in your structure. So I have explained this type of a question in the previous case using oxalic acid, if you can remember, right? So in oxalic acid, we took that as C2O42 minus, and they have given ox the abbreviation. So similarly here they have used, for the M3 plus, they have used ethylene diamine, which is we say bidentate ligand, because if you have like chloride or I minus or SCN minus, they are monodentate. They can give only one lone pair. But ethylene diamine, you see, from two nitrogen, it can give two lone electrons. So it is called bidentate. So this question is very simple because you have the element that is M3 plus given as octahedral geometry. And if you can remember, we tried to draw this one last time as octahedral geometry. So this should be the plane for the octahedral geometry, and on top and bottom there is one. So ethylene diamine, NH2, CH2, CH2, NH2 can coordinate to the metal like this, M. So this should be one like En. So for octahedral, how many En molecules you need? If this gives two coordination sites, you need 3 En molecules. So it could be En like this, right? This could be one of the coordination sites, if you think, right? So the simplest way to draw this is this one. So you can draw this one as this En site and this one as this En site. Okay, so this is our octahedral geometry. So you draw this in. And this one in this way. These are the plane. It is En. You don't have to put arrows. So you nicely see the octahedral geometry 1, 2, 3, 4, 5, 6. And this is plus 3 because ethylene diamine also there is no charge. This is neutral in form. Okay, so this is your structure. So you can see how simple the last part is, but the previous part is very easy, but you have a critical point to identify the oxidation state of the metal, like here in the compounds. So that is done. So part A of question number 10 is done. So we will move on to part B very quickly. So you are provided with the following, like 1 mole MLD minus 3 of aluminium 3 plus, copper 2 plus, and iron 2 plus, and aluminium copper Fe metal rods, chemicals required to use salt bridge, very nice, conducting wires, yes, and beakers. In addition to about the following data is provided. So for each of these metals, they have given the reduction potential of the electrode. Diagram 3 electrochemical cells that can be constructed using the above materials indicate anode, cathode along with their signs in each cell. So this is very straightforward because since you have given 3 electrodes, you can draw one using this, one using this, and one using this. Those are the only possible ways to draw electrochemical cells. So you can easily draw 3. In this one, you can use this one as the anode and this one as the cathode. right? So I will just try to use same colors. Okay. So in this one, you can use this one as anode, this one as cathode, because this reduction potential is more negative. In this one, you can use this one again as anode because it's more negative, and this one as cathode, right? And finally, in this one, this is more negative, so you use this one as anode and this one as cathode, right? So you can draw this, but they have cell diagram, so you have to like draw this one like this, and you have to show the salt bridge in each, and in this one you have to show the metal first. So I will try to do the first one, this blue color one. So my anode is aluminium, so I will put this one as aluminium, and then my solution should be aluminium nitrate, which is they have given here, and you have to mention the concentration as 1.0 MoLDM minus 3, right? And here then it should be if this is anode, this is cathode, so this should be iron, and my solution should be what is it, ferrous nitrate, FeNO3 twice, right? So we have given these beakers, and you can like put this conducting wires, that's all. So you can draw this 3 times using three different, so you can finally get it. For each electrochemical cell drawn in part 1 above, give the cell notation, so you know. So I will do for the first one, so you always know. First, you have to balance this chemical equation. For an example, if I take this one, which is our first electrochemical cell, so you know aluminium is the anode, so aluminium solid will give aluminium 3 plus aqueous plus 3 electrons. So what is the reduction? Iron 2 plus, which is our cathode reaction, plus 2 electrons, giving iron solid. But don't forget, you have to balance this in order, right? So here 3 electrons, here 2 electrons. So you can multiply this by 3, giving 3, 3, and this one 2, giving 2 and 2. Then you can write down the overall cell reaction. And in the cell notation, you can mention aluminium. It is very important to write down the cell notation very nicely, otherwise it will be a big problem. So first I will write down the anode here. So aluminium solid, phase change, aluminium 3 plus, aqueous, then the salt bridge, and iron 2 plus, but don't forget aluminium 3 plus aqueous. There you should mention the concentration as well, 1.0 MoLDM minus 3. Then the salt bridge, then Fe2 plus aqueous, comma 1 MoLDM minus 3. Phase change, Fe solid. So likewise, you can mention all these cell notation for each of these electrochemical cells. Then you can determine the cell potential, E cathode minus E anode. So for this particular example, my E cathode is Fe2 plus, so it will be 0.44 minus 1.66 volts, right? 0.44 minus 1.66. So this will be a positive value, this will be a negative value. So it will be 1.22 volt, which is a positive value. Give the balanced chemical equation with physical states for the electrode reaction. So it is what I have written here. So you have to write everything. Okay. This is very important to understand. But don't forget, in this one, you have to write this as equilibrium reactions, because we have not connected this here using a voltmeter or anything, because they have only given the conducting wires. So this is not here. Okay, so we are not getting a cell reaction actually. So therefore, you cannot write down single anode reaction, cathode reaction. You have to write all the anode, cathode, and the overall reaction as reversible reactions. That is the important here. Okay, so even you don't have to write down the overall, just they have explained the electrode reaction, so you can write down the anode and cathode. That's fine. Giving reason, explain which of the following compounds are appropriate to use in salt bridges. But don't forget, so you have to do all these steps for these 3 electrochemical cells. Okay. So whether these are good for salt bridge. So NaOH is not good for salt bridge because salt bridge mean it is normally used to make the conductivity like in a similar form, homogeneous, and to neutralize the ionic, to maintain an ionic equilibrium, right? So if you use NaOH, there will be OH minus in this solution. For an example, then if you have like Fe2 plus, it can combine with this OH minus and form ferrous hydroxide or ferric hydroxide and get precipitated. So this is not good because metal hydroxide can be formed. And NaNO3 can be good because there are no electrode reaction that can happen with NaNO3 since it is a salt. But since their conductivities are different of Na and NO3 minus, it cannot be used. So you can take this as either it can be used or cannot be used. In the evaluation, when I check the evaluation, they have given these 2 answers as well. Either if you write this can be used, you have to mention whether there is no effect for the electrode reaction. If it is not used, cannot be used, you can just write the conductivities of these 2 are different. And acidic acid automatically you cannot use because this is a weak acid and it will give very little amount of ions to the solution. So the conductivity in the solution will be very, very poor. Okay. So that is how you can express these things. Right, so we are at the last question. So consider the electrochemical cell which shows the highest E cell initially. So when you check this electrochemical cell that is indicated here with the blue color, and the electrochemical cell when you consider using the red one and the green one, and then when you try to get the potential, you will see that the maximum potential is shown by the first one using aluminium and iron. Okay, so they are telling consider this electrochemical cell which is using aluminium and iron, which I have drawn here. Assume that this electrochemical cell has been constructed using equal volumes of the relevant solution. So we are using 1.0 m, let's say 10 cubic centimeter for an example. This is also 10 cubic centimeter. Just to imagine, let's say this as V or V. Okay. And this volume does not change during the experiment. The 2 electrodes in this cell were connected using a conducting wire. After some time, the concentration of metal ions, so this was connected now. And the concentration of metal ions in the anode compartment was found to be, after some time, the concentration of metal ions in the anode compartment was found to be CmOl Dm - 3. So initially we used 1 m of each, right? So after some time, the metal ions in the anode compartment was found to be CmOl Dm - 3. Express the concentration of metal ions in the cathode compartment in terms of C. So what is the anode reaction? Anode reaction is normally aluminium. So we will try to use the word for this one, okay? Because it will be easy for me to analyze this, right? So according to this question and our electrochemical cell, right? So this was our reaction. 2 aluminium 3 plus. No, it was 2 aluminium solid maybe. Yeah, because the aluminium is the oxidation. So aluminium solid plus 3 Fe2 plus reduction. I'm writing the overall reaction. Okay, 2 aluminium 3 plus, which is the oxidation. This is aqueous. and 3 Fe solid. Okay, so I have to first write anode, cathode, then multiply the electrons to equalize, then add, so you get this one. Okay, so the question says, so initially we use where is it? Yes, this one. 1 MOLDM minus 3 of this, and 1 MOLDM minus 3 of this. Because in the solution that we have in our electrochemical cell is this. So this is aluminium 3 plus, this is Fe2 plus. Both are 1, right? So it says after one, like certain period of time, right? The concentration, I will check after some time, the concentration of metal ions in the anode compartment was found to be CMOLDM minus 3. So in the anode compartment, which is this one, after time t is CMOLDM minus 3, right? And express the concentration of metal ions in the cathode compartments in terms of C. So they are asking what is the concentration here in terms of C. So this is the question that they ask after some t time. This is CMOLD minus 3, and they are asking, try to explain that in terms of what is actually happening, right? Because what you have to understand here is in anode, right, aluminium 3 plus is oxidizing. So in anode, it should be 1 MOLDM minus 3 plus something, right? In cathode, since Fe2 plus is get reduced, it 1 minus in cathode, 1 minus something is going to reduce. That is what you have to understand here. Okay, so we have to check that using the amounts, the stoichiometry. Okay, so how do you get that one? That is very important. So here in aluminium 3 plus, the concentration is increasing in the anode compartment. Here the concentration is decreasing. So initially here the concentration is decreasing here. So 1, let's say 1, the concentration is 1 minus, let's say the reacting amount is X here for an example. We don't know. So what should be the amount that is forming here? Because this is the amount that is going to react. So what is the amount of aluminium 3 plus that is formed? Because this should happen according to the stoichiometry of the reaction, right? So the amount of X that is going to be formed here plus 1 plus, this is the amount that is reacting, X. So what is the stoichiometric ratio? X over 3 for 1 Fe2 plus, and the aluminium 3 plus is 2 times. So this should be 2. So the concentration after time t here is 1 minus X over V, if you take the volume as V, and if you take this as 1 mole. And here it should be 1 plus 2x over 3. And this is over V. Concentration. Right? Now, how do you express the this is cathode here. I will write this one as cathode, and this one as anode. Because anode compartment, the concentration is increasing. So this is what I have mentioned. So how can you express this in terms of C? Now they are telling in anode compartment after time t, the concentration is C. So I should know this 1 minus X over V in the cathode. This is cathode, right? This is cathode concentration, So I have to mention this concentration in terms of C. I don't know. So how do you calculate that? Because I know the concentration of anode compartment after time t. So anode concentration after time t is C, which should be equal to 1 plus 2x over 3. Okay. So you know this one. You can solve 1 plus 2x over 3 over v. So you can solve this one, or you can just take this concentration as y, and you divide c by y, so you can have a relationship between x and v. You can see, or either you solve this and find a relationship for connection with x and v, and you plug this here in terms of c to get the product. Okay. So it is very clear. So the anode concentration C is 1 plus 2x over V. Okay. And cathode compartment is this. So you can calculate x over V. So what they have done is they have get an x over V ratio, and they have plugged this here to get the Y concentration. So that's it. So the only difficulty here is understanding that the anode concentration is increasing after time, because this is an oxidation, this one. That is why it is plus. And in the cathode, since this is a reduction, the concentration here is decreasing. That is the only thing that you need to understand here. Then you can do the calculation and find easily. Okay. So I hope I am done with this explanation and everything. So I am finished here.